to tell you some interesting math shortcuts, tricks, parlor tricks. And I'm going to begin with one that I learned when I was in seventh grade. I was going to one of those like kind of grade school math competitions. And my dad, who is a very bored and very socially proud man, said, "Hey, do you know how to work square roots longhand?" And I said, "No, because they don't teach this in school anymore." And when I show you, you'll see why. How many of you would recognize the square root of 2 if you did it on your calculator and saw that? Right? It's about 1.4142136, something like that. So here's the way this works. So we'll practice a couple of these. I want the square root of 2. So let's play the algorithm first. What's the nearest square root of 2, like the Price is Right, without going over? 1. 1. That's right. Now, from here on out, it looks something like addition, but it's a little strange. What you do is, so we have a 1 here. 1 squared is 1. And you drop the next, not 1, but pair numbers. Whatever this is, double it and leave that blank. Because next thing I'm going to have, whatever I put up here, it has to be here. This will be 20 something. Off the top of my head, I would think 20 goes 5 times into 100, right? That's not going to work. So I got to put 5 there. So I'm going to do 4, 96. Subtract 4, drop your next pair. Whatever's up here, double it. This one's a little easier to tell. 280 something and 400. That's going to be plus. That's a 1. 119. Drop the next pair. Double that. That looks like about a 4, doesn't it? So that's going to be on 6. And it's already getting out of hand, right? But look, I've got it so far. Right? Let me do another one here.
Why did you go 24 instead of 25 on the first step?
Whatever, because 25 would be too big. If I did 25, that'd be 125, right? It's got to be less than what this is. So if I'd gone 5 here, that would have been 25.
So it's the number that you choose times the.
That's right.
Okay.
That's exactly right. So let's do another one now. Practice. 36,705. I think I did. Let's do one that's a little bit bigger. So what you do is you count this off in pairs in both directions from the decimal, right? So the decimals kind of mark the place. Nearest square root of 3 without going over 1 again, right? Double this blank. I'm thinking that's looking like a 9 thing. So it's going to be 1, 6. Barely made it. Drop the next pair. Double that. Once. Right. Next pair. Double this. And what does that look like to you? Maybe a 7's too big. Is 6 too big? I think 6 might be a little too big. I think this is 5. Let's try 6. 6 is 6 carry the 3, 15, 1, 25. Nope. What did I do there? 6 carry 3, 15, that's 9, carry 4, 22. Okay, 6 was a little bit too big, so I'm gonna go to 5. So 5, 12, 1, and this always works. And this always gives the decimal expansion. I showed this to a couple of friends when I was first or second year graduate student, and they looked at me and they said, "You are on drugs. This does not work." Right? And we sat there playing with it. You know what's the great thing about math is then after that, when they got confounded by the fact that it kept working for what they saw on the calculator, we proved that this is true. Anybody got an idea? I mean, how many of you think this is a totally weirdo algorithm, right? Right? I mean, you start off with taking the nearest square, but then after that, it's like division, but you drop 2 things, you double it. What's that all about? Any ideas? And why do you have to repeat whatever number you got right there? I'll give you a hint. What you're getting is the next decimal place at the time. Agreed? So suppose you got 10 in plus k, where k is between 0 and 9. This is sort of like adding the next number, right? So we'll get the next. What happens when you square this? This is right, 20. Okay. Everybody agrees? That too is why we double the number at the time, the 20, right? The 100 is why we're dropping decimals 2 at a time, right? K squared. That last one is, this is what you're getting is k squared. That's why you repeat this number. This is essentially it. Now, here's kind of the cool thing about this algorithm. Actually, this algorithm is not, any applied mathematician would say this is completely useless. And they would probably be right because I mean, it's really nothing but a parlor trick, really. But it's really cool that it works. And it's basically, this is what the algorithm is. This is 2 dropping at the time. This is doubling the number and multiplying by, this is multiplying by the last thing. Now, I've never seen a longhand cubic algorithm work out. I actually did work out one by myself one time. And I had to eat a bottle of aspirin because what happens here, right? Whoops. Square that 300 n squared k plus 300 k squared. Whoops. Squared. So you can work something out doing this kind of thing. You drop the decimals 3 at a time, and it is an unbelievable, unmitigated nightmare, right? So it's really kind of cool to work out. How many of you have had calculus? When you did calculus, I don't know what they do in there about this kind of thing. How many of you have seen Newton's method? Right, Newton's method. When I was younger, I thought this is kind of a silly thing, but Newton's method is really kind of interesting. Let me remind you, so this is kind of another aspect of this, believe it or not. Newton's method is a terribly clever way, and it works in a large class of reasonable situations. It works well. Newton's method is a way to get a root of a function from successive approximations, right? Has anybody ever done this before? So, and the idea is, if this is your nth approximation, you always start somewhere with approximate. If this is your nth approximation, you get this point on the curve, and you use the tangent. There it goes. You get the next approximation. And look how good that is already, right? I mean, it's kind of impressive. Newton's method for a lot of functions works really well. So let me kind of give you the formula here. So this is our approximation. And the idea is finding the x-intercept of this curve might be incredibly complicated. This might be something with, this might be a 45th degree polynomial, or it might be something with logs in it, or something awful like this. Whereas this is a freaking line, and finding the x-intercept, not a problem, right? So what is the line that goes through, what's the line that goes through this point with slope equal to the tangent of the curve? So and so let's see, the line is y minus f x n equals slope. Yeah. Should have written that in red, because that is the equation of the red line. I agree with it. And so, if it goes to this point, this is my root approximation. This, I'll call this xn plus 1, and the y coordinate is 0. Everybody agree with that? So I'm going to shove in y equals 0 here, and xn plus 1 equal x, and I get xn plus 1. And if I solve this for xn plus 1, I get my next stage in the approximation as this. This is equal to xn, isn't it? Yes, minus f of xn. Yeah. This is the famous Newton's method equation. And you can iterate the process, which is the beauty of it, right? So once you get the 10th approximation, this gives you the 11th. Now you got the 11th, that gets you 12. And this actually works nicely, right? So back to the square root business. Because I keep my big fat mouth shut, when I was in graduate school, I also showed this friend a friend of mine in physics, this algorithm as well, this square root thing. And he said, oh, that's very interesting. He said, it must be Newton's method, right? Right? That must be what this algorithm is doing. And the answer is no, for 2 reasons. Anybody know why this algorithm that I'm doing up here, taking the square root of 36,705, can't possibly be what you would get from Newton's method? Is that it?
It's not bigger.
Well, yeah, it's a very practical answer. This one would require you to know a little bit more about Newton's method. The Newton's method, for a lot of functions, in particular the kind of functions that you would use to get square roots, is incredibly, it converges very fast. It tends to double the number of correct decimal points at every iteration. Look at all the freaking work I have to do just to get like the first decimal point. It's awful, right? It's like death on a hot plate. So there's that. You got all this work that goes in, and every step of the approximation is only getting 1 more decimal place. But there's another reason that's perhaps easier to see. And that's this. If I want the square root of 36,705, my function would probably be this. That's the easiest function I can think of that has the square root of 36,705. And I'm digging on this derivative too, right? It's pretty easy to implement, right? Now, I don't know much, but I know that that function is going to look like this, more or less. Everybody agree with me? Let's think about what Newton's method does. I don't care where your first approximation is. Usually in Newton's method, you take the first approximation, just guess somewhere that's reasonably near the rule. So square root of 36.7, maybe I'd guess 100, right? Something like that. What does Newton's method do? It finds the tangent line right there, and there's your next approximation. Correct? What happens after that? Here's your next approximation. And your next approximation, your next. What is true when you use Newton's method to get the square root? The approximations are all too big. They're coming in from above, right? This algorithm right here gives you every next decimal place. It's actually coming in from below. So there's no way that this is smooth. Okay. Any questions on that? So yeah, so you can, this one you can win bar bets with because you can, I think in my collection, I think the newest book I have that even talks about how to do this, or at least I'm sure it was talked about in some other books that I have, but the most modern book I have where this is discussed, I think was written in the 1880s, right? And you know, why would you do longhand square roots anymore? I mean, it's easier to do it with a slide rule. And you all are all too young to know what that is. Right, so, okay. Here's another one. You know, the Romans, I learned this years ago. I got talked into, actually it was a lot of fun, talking to the JCL, you know, this is the Latin club kind of thing. It was national. Anyway, so they got a math guy to talk to the Latin club, right? I didn't want like rows of people committing suicide. So I had to come up with something that was kind of interesting. So I talked about Roman numerals and stuff, which by the way, Roman numerals are really fun, but they're not really that good to manipulate mathematically, right? So basically, I want to do this in regular numerals, but I want to show you what the Romans did to multiply numbers. And I want to do it, what they did is multiply, say, 38 times 1/9. Let's say they multiply those two numbers. So what they do is they make two columns. And I'll do this both ways. 38, 29. In this column, they take half of what's in this every time. And whenever there's a remainder, like there would be with 19, we drop the remainder, just pretend like it's not there. Right? I think I did that right. Halvesies, 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 right? And in parallel over here, you double it every time. Six, 4, and 13.8. Oh, I completely lost my mind. I knew that sounded right. Or I sounded wrong. Thank you. This is much better. And okay. So you only get when you drop down, just you cut it in half and you just can like remains right there. This terminates when you get to one. Now, look at all the entries in the right column that correspond to an odd number in the left column and add these suckers up. And I get 11 of 2. 58, 116, and right? Actually, let's check this in the other order, right? I mean, if this works, it should work with 29 in the left column as well. Well, let's have these this one. 14, 7, 3, 1. Okay. And so meanwhile, this is 76, 152, 304, 608. Again, look at all the numbers in the right column corresponding to an odd left. And again, that's kind of a strange way to go about it. Any idea why this works? Why in the world? It's like I'm making stuff up here, right? I mean, why would this even work? No, I don't know how the Romans came up with this. This is just like trial and error or whatever, but this doesn't even work. So let me point out, this is why this works. Now, what I'm going to do is I'm going to write, would everybody agree that every positive integer, I can write that in a base 2 decimal expansion, not in powers of 10, but in powers of 2. And the good news about that is in the base 2 decimal expansion, the only digits are 0 and 1. Right? So that's all I've got to worry about. So X might be, see what kind of notation I used here. Y, and of course, is on string. So in other words, I can write everything as just a collection because what I'm doing is I'm just ignoring all the powers of 2 in between N1 and N2 that don't appear. Okay, with that. Let's see how I've done this. Now, let's suppose that this one's in the left column, right? And this one's in the right column. Okay, so if N1 is, let's say that N1 is let's say that N1 is bigger than 0, right? Notice that X is even, and I keep dividing X by 2 until I get down to an odd one, right? Because that's the one that I'm going to add. What do I have to divide this by to get an odd? Well, I've got to divide it by 2 to the n1, right? So it's going to be n1 steps before I get to an odd. Everybody agree with that? So x first becomes odd in left column after n1 divisions by 2. Now, I divide this down until I get x equals 1 plus 2 n2 minus 1 plus 2 to the nk minus 7. And that'll be the first odd appearance in the left column. Everybody agree with that? Just got to divide that up. We'll do something. Now, what happens to y? Y has now been increased to 2 the n1 plus n1 plus 2 to the n1 plus n2 plus 2 to the n1 plus n2. Everybody agree? This is the top number this is the top number in the right column. It's the first time I've had that added because it's next to a line. And look at what I've done essentially. Basically, I've just taken y and multiplied by 2 to the n1. If you imagine that you FOIL this out, if you multiply x and that y out longhand, what's the first thing you're going to do? Multiply this whole shebang by 2 to the n1. And there it is, your first term. Everybody agree with that? Now, what do? Now, you divide this by 2 and drop the remainder, right? And now you're going to start this process over. So really what this is doing is it's peeling down. It's taking that n1 and multiplying this, then you get n2, multiply this, and the pattern continues. And so that's essentially why it works. It just seems a lot easier just to multiply things, doesn't it? But it is kind of cool that this works, right? And this little algorithm, just look at the odd entries and ones across from it, and you'll always get the right answer. Okay, here's one. Any questions? Okay, I'm going to throw in one for calculus, but even if you're not a calculus fan, this is mostly most of this is trigonometry. How many of you have done all the integration stuff you did with calculus, right? Remember doing that stuff, that you got to do the trig substitutions, you got to do all that business, right? Everybody remember that? Years of that. Okay. Let me give you an integral. What about you do? Right. Do something. Set theta. So this becomes something like what? U over U, which is that log absolute value U plus C, which is absolute value sum is 1, and I am very pleased with the sum. Right. Okay. What about this? Latching was easy, right? Because the top was the riveted to the bottom. Now what you gonna do?
I think there's a way to convert that into like a 1 minus, oh, 1 over something situation, and that would make it a lot easier. I mean, that's where I would start at least, and then.
Yeah, I can see that working. Yeah, that might work. But I could do that. I can make your life as miserable as I feel like doing. I don't see what you can do this. How many of you remember doing partial fractions? Oh my goodness, this isn't partial fractions. So partial fraction of functions are polynomials, right? Or is it? When you see a quotient powers, products, trig functions, the following substitution will always work. Let's say x equals tan theta. How many of you ever seen the substitution? This always works for quotients and trig. They don't teach the classics the way it is. This is actually some nice trig. I mean, wow, does this work? Well, let me draw you a triangle. Help out. I'm going to call it angle theta over 2. And the substitution says tangent, so I'm going to do that. Right? And my missing side by brother Pythagoras is that. Now, here's the deal. Notice that remember the old double angle form, right? I kind of worked it across here. Sine 2 theta is 2 sine theta cosine theta. Everybody okay with this? Read it off the triangle. The sine of theta is this, sine of theta over 2 is this of this. And the cosine of theta is this over this. So this is 2x over at 1 plus x squared. This terms sine of theta is portion of polynomial. Notice conveniently got rid of the square root. That's what the theta just helps us do. I'll do this way. Cosine squared. This is another old chestnut, right? The cosine, right? This is 1 over 1 plus x squared minus x squared, 1 plus x squared, which is 1 minus x squared over 1 plus x squared. Right. And there's always one more problem with these kind of problems, and that is we've got to deal with the theta, right? Somehow we've got to deal with that. But I'm going to take this right here and note that dx is 1/2 secant squared theta over 2. Right? So taking the derivative of this. And lucky us. Secant squared is tangent squared theta over 2. And this is x squared plus 1. So this is 1/2 x squared plus 1 theta, which gives us the very convenient d theta is there's a bit of amazing stuff going on because this turned sine theta into a portion of polynomials, it turned cosine theta into a portion of polynomials, and it turned d theta into a portion of polynomials. So you can get your shovel and shovel it all in there, and what you'll get is a quotient of polynomials, which in theory you can always solve. I mean, I'm being a little fast and loose, a little facetious there because the polynomials might be incredibly difficult to factor, something like this, but I think we got something to work out here. So if we apply this to our example here, then what this integral is going to become is 2x over 1 plus x squared over 2x, 1 plus x squared plus 1, and then 2 dx over 1 plus x squared. And when all the smoke clears from this, I got 4x of 1 plus x squared plus 1 dx. Is that what I got? That's 2, 2. Well, so I'll turn that quotient of trig functions into this quotient of polynomials, which at least looks to be nice looking polynomials, right? I mean, if you remember the partial fractions decomposition, I'm not going to go through all the details. It's not difficult to solve. It's just a little bit tedious. But you set up the equations here. If I remember right, it's a over 1 plus x, b over 1 plus x quantity squared, and then cx plus d over x squared plus 1. Multiply through by the denominator of the left-hand side, clear it all up. And really what I got was this. Let me check what I'm doing. Right. And actually, it's pretty easy to check if you don't want to like hear me now and believe me later. Just get a common denominator and multiply that and see you get 4x on top. And that's something that should be, in theory, easy to integrate. So, integral of 2 minus over x plus 1 squared dx is equal to 2 inverse tangent of x. And this, let's see, that's x to the minus 2, so it should be and there you go. So what you get, working back to the substitution here, well, I guess that will be 2 times the inverse tangent, so it's 2 theta over 2, so I should get theta. And the other bit should be 2 over go. And I don't know about you all, but when I see that integral, that answer is not gonna be my first guess. I'll just take a pot shot at it. Everybody agree with that? And by the way, this is right. This shows you what a loser I am. I actually took the derivative of it, checked if it works. But you have to do some trigonometric prestidigitation. It's the same thing. The cool thing about this is it works no matter what. You can always turn a quotient of trig functions into a quotient of polynomials. And even if I had done that sine 2 theta to you, I could have used trig. I didn't need to do it. I do not want to do that problem because it would be awful. But in theory, you can work it out. Okay, any questions on that? Questions?
Does that work if you have like sine squared of theta on the top? Or
Yes. Yeah, it'll work with powers. In fact, here's kind of the giveaway. This is sort of polynomials and trig functions in a certain sense. So powers in this will work with world products. It's a wonderful thing. There's also one. You can also do a variant of this with the hyperbolic trig functions if you really want to make friends. So you've got that option as well. Okay. Yes.
Would that also work with like what you were saying polynomials, but would that apply to like things that are like polynomials, like half powers or rational powers?
Oh, not the. Oh, you mean like the cube root of sine theta?
Yeah.
No, then you got problems. I would probably try to do a U substitution to turn it, get it out of that form if possible, which you may not. Sure. Here's another one. Who's got a calculator on? I mean, like an app on your phone, right? I don't know if you all have seen this one, but this one's fun. Everybody that's got a calculator app on the phone, take it out and put a number in it. Don't tell me what that number is. Now, another thing, make sure your calculator is in radians. Everybody in the math club knows to put their calculator in radians, right? Make sure it's in radians. Now, whatever that number is, take the cosine of that number. And that'll give you a new number, right? Take the cosine again, and again, and again, and again. Keep pushing it. Yes.
Can you repeat those instructions?
Yes. Put any number into your calculator that you want. I don't care what it is. Take the cosine of that number. Right? Just press the cosine button. Take the cosine again and again and again, and just keep doing that a whole bunch of times.
Oh, I didn't like that.
Just take the cosine until you are blue in the face.
Just keep it. No. It's fine.
Now, look at the numbers I wrote on the board. Anybody in disagreement with me? Doesn't matter what it is. This actually, the fact that this works is actually an important thing in, for example, dynamical systems. No matter what you started with, when you keep pushing that cosine button, you will get closer and closer to this number. By the way, I don't mean that this goes on. Anybody know how that works? No matter what you did. Yes.
Are you just taking the number mod I essentially, or not be
That's not quite it. No.
no?
Yeah.
Just a fixed point.
That's exactly what it is. It's fixed point. So cosine x, we've been sketching for a long time. does something like this. Right? Y equals X is something like this. I don't know how good my scale is on this thing, but at any rate, there's only one point where the line Y equals X and Y cosine X. Meet, right? So you put in some number to your calculator. That's your original number. And you press the cosine button. So that gives you this y coordinate, which if you had picked X the way I drew it, it would be slightly negative. Right? Now, take this over to Y equals X. And now what you're doing is now the Y coordinate here, which is what your cosine is the X coordinate here. Plug it in again. And you have that. So now your second number looks like, if you did it like me, would be positive. Everybody agree? Now you're going to plug it in again. So you're changing your Y into an X and you get here. Now look what starts happening. Plug it in. And if I draw this even better, we see that it starts to cycle in. So that's essentially why that works. I really should have drawn better cosine. But that's what happens is this point here sucks that in. You keep pushing it, and no matter where you start on this, even if you start way over there, after one iteration of correction, you will always go in toward this number. And this number is actually the only solution to cosine X. Okay. Any questions on that? Any questions? Okay, I'll leave you with one more. And I suspect most of you have seen this, but it's be nice to end on a fun note. I like divisibility. $1,245. What is this number divisible by? Some small frowns. Is it divisible by 2? How can you tell? Right, that's kind of an old chestnut, right? I mean, you just look at the last digit. If it's even, it's divisible by 2 and 9. So it's divisible by 5. Is it divisible by 3? How do we know that? Is it divisible by 9? It is not. Do you all know that the same trick works for 9? If you add up the division, it's divisible by 9 if and only if, when you add up the digits, it's divisible by 9. If you add up the digits here, you get like what 12, which is not divisible by 9, but it's divisible by 3. So this animal is divisible by 3, but not 9. Is it divisible by 11? How many of you know the 11 trick? The 11 trick is if you add the alternating sequence of digits, right? In this case, 1 minus 2 plus 4, which is 3 minus 5 minus 2. Is that divisible by 11? No. Right. So, for example, this one is divisible by 11 because the alternating 1 minus 3 plus 3 minus 1 is 0. How many of you knew that trick? That trick actually, do you know why that works? Do you know why the 9 and the 11 trick work? And the 9 one's easier because you just add up. None of it's alternating. Anybody know why those work? Because what base do we usually do our numbers in? That's a base 10 representation. 9 is 1 less, and 11 is 1 more. you always get that alternating and straight up trick in any base. So if you wrote your number in base 6, then if the sum of the digits is divisible by, well, it'll be divisible by 5 if and only the sum of the digits is divisible by 5. And alternately, the alternating sum is, well, it's divisible by 7 if the alternating sum is divisible by 7. So, but of course, it's obnoxious to have to convert it into base 6 anyway, right? So why don't you just divide it by 7 in the first place? Yes.
We multiply it by 11, but multiply by 10 and 1. And so it's shifted over. When you alternate negative, positive, every digit is going to be negative ones and positive ones on the shifted version.
Yeah, that's right. That's right. That's essentially it. That's essentially it. Good. Okay. That's what I have. Any questions about that? Yes.
Your division algorithm, it's not division, your square root algorithm, does that work for any base? Like, you have a different.
Oh, man. You even square root in base 6 now? No, I don't know the answer to that, but I mean, you should be able to do it. But what's gonna happen here is, remember how I did like the 10n plus k business? Well, now if you're in base 6, it's gonna be 6n plus k. So, you know, good luck with all that, right? So it's gonna be kind of hard probably. So, but yeah, you should be able to revamp it for another base. Yeah. Okay, other questions? Yes.
Yeah, do you mind if I ask about this solution to cosine of x equals x? That's not an algebraic number because this was no, so you're not going to have a closed form.
Don't ask me that question because I don't know. Because I think that what do they call that number? The one that's like the difference between the log and the partial sum of the harmonic series. Is it Euler's number or something like that? I don't think they even know if that's rational or not. So if you put a gun to my head and made me guess, I would say it's probably transcendental, but who knows? I don't know. I don't know for that.
What's the divisibility rule for 13?
What's that?
What's the divisibility rule for 13?
Oh, well, I can give you a real good one, base 14, but 13 by itself, you know, and really the behavior of 13 mod 10 sort of governs things, right? 7 is really bad mod 10 because it goes through a large dance mod 10, and that's why it's hard to tell. So 7 is difficult in base 10, but it would be a lot easier in base 8, which I guess some people actually do. So others. Okay, well, thanks for turning out. And next week, I think we're going to have Jared. It's either Jared or Ross, but mark your calendars that. Y'all have a wonderful long weekend, and I'll see you all next week, I hope.